Okay, this week's lab is on momentum and conservation of momentum. Have you covered momentum in class yet? Yes? Okay. Some of you have, some of you haven't. So momentum, specifically linear momentum, is a vector. So it has both magnitude and direction. And it's defined as the product of an object's mass and its velocity, right? So it gets the direction from velocity. Whichever direction an object's moving, that's the direction the momentum will be. And as we'll see, this can be kind of thought of as a store of force. When force acts on an object over some length of time, it goes into changing its momentum. Okay, so we can see that if we take the time derivative of this expression. So on the left side, we take the time derivative dp dt. And on the right side, we take the time derivative. And assuming mass doesn't change in time, then we just have dv dt on the right. And what is the change in velocity with respect to time? It's acceleration. So this is ma. And we know ma is f. F equals ma, right? Newton's second law. So evidently, the force on an object equals ma equals m dv dt equals dp dt. So force equals the time rate of change of momentum. Or said another way, the change in an object's momentum will be equal to the force exerted on it times the length of time over which that force acts on it. Okay, so this is also called the impulse that an object gets from a force. So if we use Newton's third law, it says if you have two objects interacting, then the force that object 1 exerts on object 2 is equal and opposite the force that object 2 exerts on object 1, which we can write like this. And we look at the change in momentum of two objects that interact. Their total momentum during the time over which they interact could change. And that change would be the sum of the change in the first object's momentum and the change in the momentum of the second object. And the change in momentum of the first object is equal to F12 times delta t, the force exerted on object 1 by object 2 over the length of time that they interact. And likewise, the change in momentum of object 2 is equal to F21 times delta t. So these two objects that collide, interact over some length of time delta t, they exert forces on each other that are equal and opposite. So these terms have to be equal and opposite. We can replace F21 with minus F12. And what that says is this term, which is a change in object 1's momentum, and this term, which is a change in object 2's momentum, have to be equal and opposite. Right? So if one object gains momentum, the other object loses the same amount, and vice versa. Or said another way, the total change in momentum is 0. Right? That's conservation of momentum. It says when two objects interact, the momentum of the total of the system doesn't change. So we want to verify that today using a system of two objects. And this can be generalized to more than two objects, but for today's experiment, we'll just use two. Okay, so we will do our experiments over where the computers are. Take a look over by the computers. You'll notice we have 5 computers and sort of 3 areas for you to work. So one of the areas has 2 of these cameras. These are just webcams. They're pointed straight down. And the idea is that 2 groups, you can use 2 computers here. We'll do an experiment, record it with the cameras, and these 2 computers can record the same experiment at the same time. Okay, so they're grouped 2, 1, 2. The experiment will involve rolling 2 steel balls together and having them collide and bounce off, like this. Okay, so 2 balls will roll together, collide, and bounce off, and we'll capture that on video directly to the camera, or to the computer. So we have these little tracks that you can use to get the balls to roll smoothly. So you can position the 2 little ramps, place the balls on the ramps, let go, and hopefully they will come together and collide and bounce off. It takes a little bit of timing, a little bit of luck, to get a nice collision that occurs directly under the camera. But if you don't do it the first time, just keep trying. And after 3 or 4 times, you'll probably get a nice collision where the balls come together, collide under the camera, and then roll away. So we're going to capture this video directly into Logger Pro. You can open up Logger Pro, tell it you want to import or capture a video, and then the lab manual describes the specific steps, but you can go ahead and run your experiment. It will record it. You tell it you're done, and then you can go and analyze the video data. So the very first thing you're going to want to do is take a meter stick and place it on the floor. And that's so that we can calibrate distances. So in our video, we're going to have these balls moving, and we'll know the time step of the camera, the frame rate of the camera. But in order to know distances, so that we can calculate velocities, we need to have some reference. So just take a meter stick, set it on the floor, start your video, and then you can move the meter stick. You don't need to keep it there. You just need it there for at least one frame. And so in your video that you have after you've recorded it, the first thing you're going to do is calibrate distance using this meter stick. So the lab manual describes the individual steps, but the first step is going to be calibrate distance. There's a button you press to tell it you're calibrating distance, and you drag the mouse some length, and it asks you what distance that is. So just drag it the length of the meter stick, and then tell it that equals 1 meter. And then Logger Pro will go through the process of calibrating all your distances relative to that. You're also going to be able to set an origin. So if you want, you can set an origin of your coordinate system. This might be a good spot. You can choose the orientation of your coordinate system as well. You don't have to align it to any particular axes, but if you want, you can make it so it sort of goes along the direction of the balls, or not if you don't want to. And then you go through and you digitize the motion. So you can take the playhead or the video player and drag it to the point where the first ball comes into the frame. Okay, so when you start this, if this is what your webcam is capturing right here, you should start the balls outside of the frame. Right? You don't want to start them here, because then by the time they're going, they've almost collided. You want to start them out here where they're not in view of the camera, and then allow them to roll into the view of the camera, collide underneath, and then roll completely out of the frame. And so you advance the playhead to the point where the first ball is on the frame, and you keep going until the second ball is on the frame. So once both balls are on the frame, that's when you start recording data, and you will click the center of the first ball. And after that, it will update to the next frame, and you'll click on the center of the ball again, and it keeps advancing the video, and you keep tapping where the ball is, and as you're doing this, it's recording your mouse clicks and calculating the trajectory of the ball. And it's populating a column of data for the x and y position of the ball. And then you'll go through, you'll do the same thing for the second ball. So again, detailed steps are in the lab manual. When you're done, you'll have a series of points superimposed on your video that represent the spots where the ball were each 15th of a second, if you have a 15 frames per second camera. And you'll have a data table filled with the x and y positions of ball 1 and ball 2. It also calculates the x and y velocities of the balls, because it knows the frame rate. It's communicated with the camera to figure out the time between these frames, and so it's already done the process of taking the difference in position, dividing it by the time to get a velocity. Okay? What we don't have yet is momentum. So momentum is mass times velocity. So you need to take the balls, put them on the scale, weigh them. You can enter those masses as parameters, and then you can create a column for the momentum in x, the momentum in y, for ball 1 and ball 2. We'll then add up the total momentum. So when we're adding up vectors, we add up their components. So we'll get a vector for the total x component of momentum and the total y component of momentum. It'll come just from summing the x component of ball 1 and the x component of ball 2. The y component of ball 1 and the y component of ball 2. and then plot these things. When you plot them, what you will probably notice is that the x and y components of the momentum are not constant. They're likely changing in time, roughly linearly, either slowing down or speeding up. And we don't care about the overall change in time. We care about what happens at the collision point. So we're going to look for any changes that occur sort of right in the middle of the video where the balls collide. But it's going to be hard to analyze what happens at this point in time if the overall momentum is changing throughout the entire experiment. So we need to correct for that. First, do you know why the total momentum might be changing? Particularly if we say momentum is conserved. Why would we run an experiment and find that the momentum is changing? So momentum is conserved between the two balls. So the only forces that we're dealing with are the forces of interaction between the balls. Momentum is conserved. What other forces are going to act on these objects during our experiment? Friction is one. So if you see an object slowing down, it may just be friction. And why might an object speed up? The floor is not flat. In fact, it's fairly significantly not flat. If you simply set the ball down, it will start to roll. Okay, and if you were to try to analyze that, you might assume there's no forces acting on it, and then it starts to move, which is a violation of Newton's second law, his first law too. Okay, so we need to account for these external forces that act on our system that aren't part of our intended analysis. And so the way we're going to do that is we're going to take these curves and we're going to straighten them out. Because we don't care about the overall trend, we just care about what happens at this point right here where they collide. So the way we're going to straighten them out is we're going to do a linear fit. Tell Logger Pro to give you its best fit line, and then just record the slope. And what we're going to do is we're going to add to this line an offset that has this form. And when we do, these tilted lines are going to end up flat. If there's a jump in the momentum at the collision point, there will still be a jump down here. There just won't be an overall trend. Okay, so your data should look like this after you've corrected for that slope. Again, the steps are in the manual, so I'm not going to go over the details of how to do that. Just I want you to understand why we're doing that. Okay, and then at this point, we also want to know when the collision occurred, because we're going to be looking for changes in the momentum, and there's always going to be noise. So we're going to ask if there's any changes in the momentum that are bigger than the noise. But we need to know where to look. And so on this graph over here, you should count the number of data points until the balls collide. Or find the time at which the balls collide. Okay? And then you want to shift your time axis by that amount so that 0 is not the beginning of the video, 0 is the point where they collide. Okay? So you just make a calculated column. Take the old time, subtract the time they collide, and that will be your new relative time that you can make all your plots versus. So that tells the person looking at the plot when the collision occurred, and we're going to look for changes in the momentum before and after that point. Okay, so you will have the x and y components of momentum, but I want you to do this in terms of the magnitude and angle. Right, so you know how to get from the x and y components of a vector to its magnitude and angle, right? Use the Pythagorean theorem to get magnitude and use the arctangent, some trigonometry to get the angle. So plot those versus time. These two plots will go into your lab report. These plots don't. This is just for these are steps along the way. These are the results that I want in the lab report. And we want to analyze whether there was a difference in the momentum before the collision and after the collision. So to do that, you'll take your mouse and click and drag over this region here before the collision, right? Before t equals 0. And it will draw these little bars, or these brackets around your data. And then if you ask it for statistics, you go to the Analyze menu, Get Statistics, it will tell you the mean value and the standard deviation during this time. Right? So your mean value, that is your measured initial momentum. or the magnitude of the initial momentum. And the standard deviation is your uncertainty. And then you can do the same thing for the final momentum. So click and drag over here and highlight this region of the graph. And again, go and get the statistics for that, and that'll be your final momentum and uncertainty. So you know how to compare these things. These are two quantities that we expect to be equal within the uncertainty. So ask if the range of this and the range of that overlap. If they do, then you've shown momentum is conserved. If they don't, you've shown it isn't. So do that for the magnitude of the momentum and do that for the angle of the momentum. Okay, one thing you have to watch out for.